In this video, I introduce using KL-Divergence to effectively train GAN models. Traditional generative models rely on maximizing likelihood of output samples, or equivalently minimizing the KL-Divergence between the unknown data distribution PR and the generated distribution PG. If the distributions PR and PG are continuous and described by two density functions PR and PG, respectively, the generative models are trained by minimizing the KL-Divergence, which is integral for PR times log over the domain X, which has a unique minimum at PR is equal to PG. KL-Divergence doesn't need to know the true distribution PR, and instead relies on the training samples. If PR larger than PG, X is sampled with a higher probability from the real data distribution than from the generated model. If PR much larger than PG, we will see mode dropping. If PR is smaller than PG, X is sampled with a lower probability from the real distribution than from the generated model. In this case, the generated sample seems fake looking. GAN generates realistically looking images due to the switch from the maximum likelihood estimate to distance measures between the real and the generated distributions, which is formulated in two steps. In first step, we train discriminator D to maximize the loss function LD, which is the sum of two expectations. In the first term, X is sampled from the real distribution PR, and in the second term, X is sampled from the model distribution PG. This D is a probability of a fake sample. The optimal discriminator has the shape here. The optimal value is reached when the PR is equal to PG, namely, optimal value D star is equal to 1 over 2, which is substituted into LD. We have LG for the generator training, where this is the JS-Divergence for the optimal D star, minimizing LG with respect to the model parameters state, leads to JS-Divergence to train the generator G. The maximum of discriminator D is reached at 2 times log 2 minus 2 JS-Divergence only if PR and PG are not continuous or have a disjoint support. In this case, JS-Divergence is 0, so the generator cannot learn anything. First, let's take a look at PR and PG are not continuous. The support of distributions PR and PG lie on a low-dimensional manifold. For example, support of PG is contained in GZ. If GZ has a less dimensionality than X, PG is not continuous. PR and PG have a disjoint support. For example, a discriminator D satisfies PR is 1 and PG 0. In this case, the discriminator D is easily trained, but the generator G learns nothing because of vanishing gradient. For example, discriminator D is easy to distinguish its input sampled from a real distribution or from the model distribution. Because this probability D is 1, so 1 minus D 0 means loss function for generator is 0, so we cannot use this loss function to train generator run anything. The solution is to add a noise in the input of this combinator to smooth densities. However, the noise will degrade the quality of samples, or the noise distribution is used as a prior of the generator. When we pass gradient from the discriminator to generator, the loss function of the generator determines GAN behavior. Generally, when the discriminator becomes better, so that the probability D of the real sample tends to 1. Therefore, 1 minus D is 0, namely the gradient of the generator vanishes. What again training can reach is Nash equilibrium, namely the D is equal to 1/2, which is a very hard job. To avoid the gradient vanishing, we change the loss function of the generator to negative log D, which makes the generator and the discriminator moving in the same direction during the GAN training. The idea is shown here graphically. For more details, please check with these references. Thank you. Bye.